a classic fuzz, the Big Muff. Designed in the 70s, used by Hendrix, Gilmour, Smashing Pumpkins. Very popular fuzz pedal. It's actually 4 gain stages put together. So I pulled up the schematic here. And so this is the input. And we come to this area here, which is a straightforward gain stage. It's pretty high gain. And then it's got some feedback, negative feedback, it looks like here through R9, and then some caps to filter and give this gain stage a tone shape. And then we pass through this capacitor here, and then we have a potentiometer, 100k log, and this is labeled sustain, so that is this guy here. So this allows the amount of signal that passes from this gain through to here. There's a minimum amount of signal that gets through, defined by R1. And then we have 2 stages here, and these are the clipping stages. So again, we've got some reasonable amount of gain on both of these, but the negative feedback this time has 2 diodes in each one, 1N4148s, 1N4148s. There's a lot of mods around on the internet where you can change these diodes to either LEDs or silicon diodes, which changes the clipping characteristic. So this, you know, essentially, if you imagine there's an op amp here instead, it's kind of a soft clipper circuit. And then finally, the 4th gain stage is here. A lower amount of gain is applied at this stage, and it comes after, or I would say it's probably designed to compensate for the tone stack, and this is a tone here, so that is this potentiometer here. And you know, it amplifies, it enhances the brights at the cost of the bass signal, or amplifies or enhances the bass at the cost of the treble signal. So that's what this tone button's going to do, or tone pot's going to do. Passes through this capacitor, and then we have the final stage here, which I just said is a lower gain stage, and it is connected to this pot here, which goes out to the output jack here, which is labeled amp. And on this specific version, the tone wicker, you can actually bypass, and this is another mod that is on that you can find on the internet, but it's actually a standard feature in this particular version of the Big Muff, and that's one of the reasons why I own it. You can bypass this and it'll give you a lot more gain. The signal will become a lot more flat as well. And then it's got this tone wicker feature, which is kind of a tone enhancement. So there's a switch here. So when I flick this switch, which is this switch down here, it actually makes all these contacts here, this one, this one, this one. This is what the chip does. It's a chip switch. And so what it's doing is introducing a capacitance here, here, and here that is connected to the output, and creates another kind of feedback loop, or a capacitive, a frequency dependent feedback loop. So that's what this switch does here, the wicker switch. So I've got it hooked up to a signal generator, 1 kilohertz sine wave as usual, into the input. Output goes to the scope. We've got that on channel 4. We've got a volt per division right now. And then I've got it hooked into this 9-volt power supply here. So why don't I just switch it on? And everything on max, you can see this is our distorted signal. So we've got 1, 2, 3, 4, 5, 6 at a volt per division. So maximum swing, maximum output voltage in this is going to be 6 volts. If I remove the tone stack, look at that. So that's an unshaped waveform, and so this is with the tone enabled. So I move the tone around, but there's also some filtering in there that this tone knob doesn't control, because when I remove the tone stack, we get to this square wave. So now we've got the tone stack removed and we've got this asymmetrical clip going on. Why don't I bring down the sustain a little bit? See what happens. Okay, so we never get to something that is a sine wave, so this thing's going to be clipping forever, and that's with the wicker on, so that's kind of, there's a smoothing effect going on there, but that's still a distorted signal at 1 kilohertz. So I'll turn the wicker off, turn the tone stack on, so it's like a true Big Muff. And then let's just poke through some frequencies and see what happens. So let's go down in frequency. Signal remains about the same. Let's go up in frequency. 3 kilohertz. Aha, so the distortion changes as we go up in frequency. So it's heavily frequency dependent. Obviously, there's a lot of capacitors around those transistors that we looked at in the schematic earlier. So let's go back to our reference, our 1 kilohertz. And there we go. Let's change the time base. And then it's quite nice. Raise the amplitude a little bit. That's almost a sine wave at 1 kilohertz with this setting of tone is all the way down. You see there's a massive effect on the waveform with the tone. So this one, obviously, all these guys here are higher frequency. Then we go to here. It's kind of lower frequency. It's almost a sine wave. That could be a clean boost. Let's step through some frequencies again. So we go down lower. Yeah, it's still square. It's not quite, I know it's not, there's no clean boost capability in this thing at all. But we do see roll off. So this is 1 kilohertz, nice big signal. And then go up 2 kilohertz, smaller. And this thing is rolling off now at 3 kilohertz. So that's the base end actually. So if I turn up the tone, so we're emphasizing the higher frequencies, it's still reasonably attenuated the signal at 3.5 kilohertz. So if I go down, you can see the signal continues to grow. So that gives us an idea of the frequency response of the unit. Very, as you know, if you've heard of Big Muff, there's a lot of low end in it, and there's not so much high end. And if there is some high end, it manifests itself as some fizz that we probably won't see when we're using these pure sine waves that come from the signal generator. So let's flip this thing over and get the scope probe inside and see what we can measure on each different stage. So if we just set it up, so we've got a signal there. That's kind of clipped, isn't it? I like that. So we've got 1 kilohertz going in, and then yeah, there we can see it's a symmetrical distortion, by the way. So let's flip it over and remember this signal. It's kind of a square with some sine wave riding on top. And so let's see what part of the circuit introduces that. The first area we're going to probe is the sustain potentiometer because it's easy to reach. So that's the output of the first stage. So if I just touch the probe on here, and there you can see it's, so the blue is the output of the first stage, and it's actually a really nice sine wave. So that first stage is acting like a boost, a clean boost. which is pretty neat. And then as we go into the next stages, we'll see where and how that distortion is introduced, which is the green signal that you can see there. So I've got the scope probe on R12, which is the output of the second section, and you can see the blue waveform is squared off now, and that squaring off has been caused by those diodes and how it curves, how it kind of clips off. And the clipping technique looks like a soft clipper is a combination of the diodes and those capacitors. Now if I just move over here to the next section, the third section, it's on the switch here where you put the tone in and out. I can just get on the probe on there. There we go. So now it's super square. So that sine wave, that pure sine wave that we saw in the first section, is now inverted as well. Obviously, well, it's the third section, so each one is an inverting amplifier. So first section turned it upside down, second section made it the right way around, and now the third section is inverted, and now we're super squared off. And so we're going, if we apply the filtering now in the next section, that's how we're going to get to this, to the green signal that you can see there. So this is filtering summer. Let's see what it's set at. So on the front there. So when we're here with the tone stack down, we're letting all the lower frequencies through. As we turn it up, we're letting only the higher frequency components of that square wave that was going in. And so what you see here is the high frequency component, this edge going up and then settling, is the high frequency component of the square wave going in. And that's how we create all these wonderful tones. So that's how the Big Muff works. 4 stages and a tone stack. Now, we did notice that the first stage actually makes a clean boost, so I've modified this guy as well. So this switch here on the front panel, this switch here, bypasses 3 stages and the tone stack. So if I click it in, we have a nice signal. Distortion, signal. So what have I done? I've made my massive fuzz distortion pedal into a clean boost. Now let's just talk about that for a little bit, because it's kind of clean, but remember there's capacitors in this block diagram everywhere. So there's a capacitor on the input, and that is a pretty high value. So that means it's going to let through a lot of the bass signals. And then there's capacitors on the negative feedback. So that's going to attenuate or provide negative feedback on higher frequencies. So it's going to attenuate some of the higher frequencies. So this thing is set up. If we just look at it in terms of the first stage, which we're calling a clean boost stage, it's going to emphasize the lower frequencies and have not so many high frequencies. So I will call it maybe a warm clean boost or low end clean boost. But why don't we plug it in and see what it sounds like?